Hello everyone, welcome to this video where we're going to be talking about a mechanics of materials topic, specifically applying elongation and maximum distortional energy theory or ductile failure and Euler's buckling. So first, as always, we begin with a free body diagram of our body over here. So we have a two elastic elements that are connected to ends A and B of a rigid inverted T-shaped bar ABCD. Each elastic member has a Young's modulus E, circular cross-section of radius R, length L, yield stress sigma Y. The rigid bar is pinned at C and a load P is applied at ND as showed in figure 1. Part A, assuming both elastic elements are under tension, draw a free body diagram of the rigid T-shaped bar. So the full body is going to look something like this. And we note that we have a force P acting here, and we have F1 from the first axial member and F2 from the second axial member. We also have a pin support, or not a pin support, but a support at C. And actually, I think it is a pin support. So thus there'll be two reaction forces in the CX and CY directions. So this is our free body diagram. And we're choosing the positive y-axis and positive x-axis as these directions conventionally. So we have done now let's write the equilibrium equations for the rigid T-shaped bar and the compatibility conditions that relate the elongation of the elastic elements 1 and 2. So we will take the moment around C because this is a convenient point, as if we take the moment around C, we don't have to worry about these two unknown reaction forces here. So the moment and the sum of the moment around C is equal to F1, and by the right-hand rule, it's going to rotate counterclockwise around C. So thus the moment is positive F1 times a distance of A from point C. So F1 times A. And then we have minus F2. And because F2 is negative because it's counterclockwise, it will cause a counterclockwise rotation about C. Minus F2 times is the length of 4A from C. So times 4A. And then P will also apply a moment around C. And that distance is 2A. So thus we have plus P times 2A, since P causes, again, a counterclockwise rotation about C. And thus the moment here is positive. And the moment around C, of course, must be equal to 0, since this whole shape is under static equilibrium. So we have our moment equation, and now we need our elongation equations. So let's think about how this object is going to deform. And of course, this is an exaggeration, just so that we can visualize it better. But as the P is pushing here, and these two supports are here, the object is going to deform in this following way. So it's going to bend down. And from the original direction, there's going to be some small angle theta. And thus we can use the small angle approximation. Uh, we have an elongation here, uh, E2, and an elongation here, E1. Um, and are they both going to be tensile, compressive, or what are going to be the signs of these arrows? Well, let's think about this a little more. So I think we drew the directions of the arrows correctly. One is going to be under compression when the other is under tension. That's just an intuitive fact because as this end is pulled upwards, it's going to cause as this end is pulled upwards, this other end is going to be compressed because there's this beam over here resisting the force. And over here, this beam, this member is pulling on this section. While over here, this member is pushing upwards on that section. So now we can use our small angle approximation, which says that theta is approximately equal to, or tan theta, when uh, tan theta, when theta is very small, which is about less than 15 degrees, can be approximated by theta. Um, and thus we have our elongation equation as E1 over this distance over here, which is um going to be A, as we found earlier. E1 over A is equal to E2 over this distance over here, which as we found earlier is 4A. These two distances are equal. And remember that since, sorry, not E squared. Remember that since E2 is in tension, E1 will be in compression. And thus we have our signs. Negative E1 over A equals positive E2 over 4A. And this is from the fact that tan theta is equal to adjacent um uh is equal to opposite over adjacent. So if we look at this triangle over here, we saw that we could represent it as this. So E1 is the opposite, and um adjacent was the A, and theta was here. And we used a similar reasoning for the second triangle over here. Now, another way we can think about maybe the compressive or positive signs is that E1 over here is going down as given by our sign convention here because the arrow is pointing down. Whereas for this one, it's going upwards and this one is going downwards. So we will have negative E1 over here instead of positive E1, and that will give us our negative value over here, which checks out. So now we have our elongation equation. So now we have to determine the axial force on elastic elements 1 and 2 for P is greater than 0 and indicate whether the element is under compression or tension. So now let's remember that our elongation equations are given by um E1 generally is FL over EA, where L is the length, E is the Young's modulus, and A is the area, cross-sectional area of the beam. So E1 is equal to F1 L1 over E1 A1, and E2 is equal to F2 L2 over E2 A2. And um, plugging these two E1 and E2 values into this equation over here, we will get that negative F1 F1 L1 over E1 A1 over A is equal to F2 L2 over E2 A2 times 4A. And thus, the A's cancel on both sides, and we can multiply the left side by 4 to get that 4 negative 4 F1 L1 over E1 A1 is um equal to um F2 L2 over E2 A2. So note that from the elongation, um the this the distortion of the T down and the T up will also um cause this member to be in compression and this member over here to be in tension. So this first member will be pulled and this second member, this first member will be compressed and this second member will be pulled. So we'll take that into account. But now let's plug in our known values for E, A, and L over here. So we will have negative 4 times F1, which is what we're trying to solve. We're trying to solve for F1 and F2 times L1, which will be the length of member one over here, which is equal to L over the E of member one, which is E, and the cross-sectional area of member one, which is given by pi r squared, because this member over here can be expressed as a member like so, and the cross-sectional area over here um is given by pi r squared. Um, so after that, we will plug in the known values on the right-hand side, which is F2 times L over E times pi r squared, since the values of these two members is over here equal, which is nice. Now we can solve for F1 in terms of F2. So we can cancel a lot of things here. We can cancel the pi r squared, the E, the Young's modulus, which is the Young's modulus, the L's, and we're left with negative 4 F1 is equal to F2. And thus that F1 is equal to negative F2 over 4. So now we have our value for F1. We can use our initial moment equation over here, which says that F1 times A minus F2 times 4A plus P times 2A is equal to 0. So plugging in F1 equals negative F2 over 4, we have negative F2 over 4 times A minus F2 times 4A plus 2PA is equal to 0. And let me actually just write this plus 2PA is equal to 0. And notice that we can divide both sides by A, so all the A's go away. And we are thus left with negative F2 over 4 minus 4F2, which is equal to negative 16 over 4 minus F2 over 4, which is equal to negative 17 over 4. And this is equal to subtracting negative 2p from both sides. Subtracting 2p from both sides, we have equals negative 2p. And thus that negative 17 over 4 F2 is equal to negative 2p. So thus F2 is equal to 4 over 17p. Or oh no, 8 over 17p, sorry. Because we have a factor of 2p. And using our relationship of F1 and F2 over here, we can then find F1 is equal to negative 8 over 17 divided by 4, which is negative 2 over 17p. So these are thus our axial forces on elastic elements 1 and 2 as required by part C. So now we're done with A, B, and C. And we can move on to part D. And so I have reorganized everything in a more beautiful format. So we can go over part D shortly. So for problem D, first we have to know what buckling means. So buckling basically is when um wait, sorry. Buckling is when the beam is distorted. For instance, buckling will happen when the beam bends this way, or potentially the beam can bend out of the plane, which is in the positive z direction or negative z direction. Positive z direction will be pointing out, negative z direction will be pointing in. So if we are looking at, for instance, our YZ plane, the member has the potential to bend either this way or this way. That is what buckling means. So then, for Euler's buckling theory, the P critical can be calculated by this expression over here. So P critical is equal to pi E I over L effective squared. And notice that member 2 will not have any buckling associated with it, as when the whole structure goes like this, member at B, the member at B, which is member 2, will be pulled upwards, while the member at A will be the one under compression, and thus it has the is the one that has the potential to buckle either like this or that, or out of the plane as we described earlier. And thus the P critical will only be applicable to member 1. So we can simply state that pi E1 I1 over L effective squared is equal to P critical in this whole structure. Now, it is worthy to note that if it so happened that this problem was a problem like this, where the member is over here, and P is applied, then there's potential for buckling in both of these members because now when when the whole structure distorts this way, both of the members are under compression. So both of the members has the potential to distort either like this, like this, or out of plane directions. So in that case, we will have to calculate, I believe we will have to calculate P critical for both of those members and compare those values. And in that particular case, we will have to choose the limiting factor. But this problem, because only member one is under buckling, is pretty simple. Now we also have to know what our L effective is. And from that, we have to know what types of constraints these are, whether they are fixed ends, pin joints, or what they are. Because the L effective depends on both of these ends, whether they are fixed, free, or pinned. So for that, we are going to do a little Google research, and I'm going to show you the different expressions for L effective. So from this physics stack exchange, we can see that the L effective for two pinned ends is basically just L, the length of the beam. Um, and for a fixed and free end, the L effective is going to be equal to 2L. And for two fixed ends, the L effective is going to be 0.5L. And for a pinned end and a fixed end, the L effective is going to be 0.7. So here we note that the type of structure that this is over here, the type of structure that beam 1 is actually two pinned ends. So thus the L effective for a member with two pinned ends is just equal to L, the normal length of the beam. So since the natural length of the beam 1 is just L, we will use that for L effective. And thus the P critical will be equal to pi times E1, which is simply equal to E times I1, which we will calculate uh, soon, over the L effective, which is just L squared. So now we'll be calculating the value for I1. So our moment of inertia around the centroid of a circle is given by pi r to the power of 4 over 4. And we chose the moment of inertia around the centroid of a circle because um each of these members has a circular cross section, so each member will look something like this. So we're finding the I, the moment of inertia I around the centroid, so IZZ of a circle. And that will be that will give us that P critical is equal to pi times E times pi over 4 r to the power of 4 over L squared. So our P critical will be thus equal to pi squared times E times r to the 4 over 4L squared. And this is subsequently going to be equal to the axial force, F1, which is given by -2 over 17P. So solving for our P value will give us the P critical. And I'm very sorry about this, but one thing we forgot is that the P critical formula is actually going to be uh pi squared times E times I. So the pi over here will be squared. All these pi's will be squared. And then this pi will be cubed. And then the P value, the P critical value, or the smallest force P will thus be equal to um so the P value will be equal to 17, or rather -17 pi cubed times E times r to the power of 4 um over 8L squared. And since they want the smallest force P, they want the magnitude. So we'll take the magnitude of P. So that will give us that the magnitude of P, the smallest value of P will be equal to 17 pi cubed times E times R to power of 4 over 8L squared. So this one will be our final answer for the smallest force P. Now we can move on to part E. And I think in this problem, we didn't consider out-of-plane buckling, which is buckling in the z direction of member 1, is because when considering out-of-plane buckling, both of these ends would be as if they're fixed. Because imagine if we have two pinned ends, but both of these places constrain this beam from bending outwards. So both of these ends, from the YZ perspective, is behaving as if they were fixed ends. Because from the YZ perspective, we have our pin over here and our pin over here, but there is something constraining it from bending outwards. Because both of these ends will be almost as if they're fixed. So for part E, we want to, when the slenderness of elements 1 and 2 is significantly reduced to avoid buckling, we want to determine the smallest force P greater than 0 that will induce ductile failure on the assembly and indicate whether it will be on element 1 or 2, and express the result in terms of material properties and geometric parameters. And they want us to use the maximum distortional energy theory. For ductile failure, it is the same whether the member is under tension or compression, contrary to buckling, where it's only applicable for members under compression. We can thus consider whether the failure will occur on element one or two. And this is from looking at which one is the limiting factor. As we can see over here, we found that F2 is equal to 8 over 17p, and F1 is equal to negative 2 over 17p. So since F2 is equal to 8 over 17p, which is greater in magnitude than F1. The value of p for F2 will be smaller um, if the if the stress in if the stress at which it fails in both is the same for each one because of the symmetry of this problem. So thus F2 is going to be the limitation for failure in this particular example. In short, F2 is going to fail at a smaller value for P. For maximum distortional energy theory, sigma m, which is the von Mises stress, is going to be equal to the yield strength. As we can see, for the failure theories, the maximum distortional energy failure theory for ductile materials is given by the von Mises stress is equal to the square root of principal stress 1 squared minus principal stress 1 times principal stress 2 plus principal stress 2 squared. So this is the equation we're going to use. And what is crucial for this problem is we have to determine what our principal stresses are. So we're going to do that shortly. So first, notice that this is an axial system. And we're gonna write our equation first for the von Mises stress though. So sigma m is equal to square root of principal stress 1 squared plus principal stress 1 times principal stress 2 uh plus principal stress 2 squared. And our stress element here, because this is an axial system, so it means that there are only axial forces in this system. And since there's no force in the x direction, there's only forces in the y direction. Um, and since F2 is positive, it means that F2 is in tension. And we are going to use F2 because it's our limiting force. So in an axial system, we have um, these are the only stresses, which is sigma y, and it's equal to basically F2 over A, where A is the cross-sectional area of the member, which is equal to 8 over 17 P over pi r squared. So um, calculating our principal stresses requires taking into account the average. So sigma average is equal to sigma x plus sigma y over 2. But since there is no sigma x in this problem, um, sigma average is simply going to be sigma y over 2. And our principal stress 1 is given by, our principal stress 1 is given by sigma average plus r. And our principal stress 2 is given by sigma average minus R. So now we have to calculate our R value. So how to do that? So in our transformation of stress for Mohr circle, our R value, which is the radius on the Mohr circle, is given by this formula over here. So this is the formula we'll use in order to calculate our R value and thus our principal stress 1 and principal stress 2. So here we have our R value, and as we know, sigma x is equal to 0 since this is in pure tension, and the stress value is also 0. So as a result, R is simply equal to the square root of negative sigma y over 2 altogether squared, which is equal to sigma y over 2. And thus, principal stress 1 is equal to sigma average plus R, which is basically sigma y over 2 plus sigma y over 2 is equal to sigma y. And sigma P2 is equal to sigma y over 2 minus R, which is sigma y over 2 too. So sigma y over 2 minus sigma y over 2 is equal to 0. And thus, the sigma m is equal to, since these two terms go to 0 because they both have the principal stress 2 term in them, which is 0. We're left with sigma m is equal to the square root of principal stress 1 squared, which is equal to uh principal stress 1. So principal stress 1 is then equal to uh sigma y, which is in turn equal to 8p over 17 pi r squared. So we can solve for p from here on. And solving for p, we have so solving for p, we have that since 8p over 17 pi r squared equals sigma y, p equals 17 pi r squared sigma y over 8. And that is our final answer for this part of the problem. Let's scroll up. Um, for part E of the problem, if the slenderness of elements 1 and 2 is significantly reduced, um, determine the smallest force P greater than 0 that will induce ductile failure. So our P value is this value over here. Okay, thank you for watching this video and see you in the next video.